And okay. And well, it is really an enormous pleasure and an honor to be able to present our research to you. So what I will try and do today is give you a global idea of what is happening in the field of early galaxies and how we think they actually re-ionize the universe. So without any further ado, let me jump into the talk. So I thought I would start by putting this whole talk into perspective. So this is our cosmic timeline that we have really painstakingly built over decades of observations. So this has been made possible by instruments which we are all well aware of, which range from CMB to galaxy instruments. So what I would like to start with is that our universe started roughly 13.8 billion years ago in something called the Big Bang. This was followed very soon after by a period of accelerated expansion called inflation. Now, during inflation, the universe was basically expanding, and as it was expanding, it was cooling. Finally, at a redshift of about 1100, which is roughly 400,000 years after the Big Bang, for the first time, the universe was cool enough that electrons and protons could combine to form neutral hydrogen. And at this point, matter and radiation get decoupled from each other, giving rise to the cosmic microwave background. Now, the formation of the CMB is followed by what is called the Dark Ages in the history of the universe. And this period, which can last a few 100 million years, is called the Dark Ages because at this point, all that is happening is that dark matter is trying to collapse to form halos, but baryons or normal matter has not yet started to cool and form stars. So really, the only photons we have in the universe are the photons of the CMB, which are now free streaming. So these cosmic dark ages come to an end with the formation of the first stars and galaxies at a redshift of 30 or 13, really depending on your favorite model for forming the first stars. Now, let me remind you that when the first stars start forming, the universe is effectively full of hydrogen, 75%, helium, roughly 25%. So I'm not going to talk about helium reionization at all today. I'm only going to focus on hydrogen. So basically what happens is that when these first stars start forming, they produce the first photons, which can break up this hydrogen around them back into electrons and protons, starting the epoch of hydrogen reionization. As more and more stars form inside more and more galaxies, these ionized regions, which you can see here with these sort of brownish patches, they start growing and overlapping until at some point they cover all of the available volume of the universe. We think this happens somewhere within the first billion years of the universe. Now, this is one of the key things that the SKA is aiming to probe, this patchy topology of reionization. What I would also like to point out is that this is the last major phase transition of the universe in its entirety. So once this hydrogen is reionized within the first billion years, it has since then remained reionized for the next 12.5 billion years. So it is really crucial to understand this last major phase transition of all of the hydrogen in the universe. So I would first like to acknowledge the work of the team in Groningen who have really led this, and I'm going to keep pointing out colleagues who have led different parts of the project. We are very heavily involved in SKA and Euclid in their theory groups. We are involved in a lot of different projects in ALMA and the James Webb. And of course, all of the work that I'm going to show you would not have been possible without the fantastic collaborators listed here. And I think Atri and Tiert are actually in the audience, so I would like to acknowledge their significant contributions. Okay, so let me start by saying that when we talk about the epoch of reionization, of course, the sources that are driving reionization are the first galaxies. And what I would say is that this is really a golden age for observing these sorts of early galaxies. So let me point out to you that till about 10 years ago, we had only a few galaxy candidates at high redshifts. But over the past decade, thanks to instruments like Subaru, Very Large Telescope, Spitzer, Hubble, and now, of course, the ALMA and James Webb, we have been able to collect enormous statistics about these early galaxy populations. So now we have more than 10,000 galaxies at redshifts larger than 5. So we can really start to do statistics, and we can really start to use these to probe the epoch of reionization. Just to give you an idea of the sorts of observables that we are able to collect, the first most basic thing is, well, we want to know how many galaxies do we have per co-moving volume as a function of their luminosity. This is the luminosity function, which has now been mapped out to as high as redshift 18. How many total stars are we actually forming in the universe per co-moving volume at these early epochs? This is the star formation rate density, which is now getting probed out to, again, a redshift of 14, 16. How much total mass is bound in stars per co-moving volume? So this is the stellar mass density. With ALMA, for the first time, we are actually, with ALMA and the James Webb, for the first time, we are able to actually probe the dust masses and metallicities well into the epoch of reionization. So I'm not going to talk about this in detail, but if you're interested, please ask me more about this. But as of now, we have metallicities for galaxies between redshifts even 10 and 13 with the James Webb. Finally, given the resolution of ALMA and the James Webb, we are able to even look at the sizes, mergers of early galaxies and even young star clusters at redshifts as high as 7. So what I would like to point out is that for the first time, we have this enormous wealth of data that can actually help us to probe our galaxy populations, which is what we, in some sense, need to understand the epoch of reionization. Now, this wealth of data has also given rise to more and more open questions, as you can imagine. So for example, some of the questions that we are trying to address are, so what are the physical properties of these early galaxies in terms of also their dust and metal masses? How was the assembly of galaxies dependent on the environment? And I'm just going to show you in a second, this is something that is really crucially tied to reionization. How did galaxies evolve through time? How did they reionize the universe? What was the feedback from reionization back on galaxy formation? I'm not going to talk about black holes and gravitational waves, but if you're interested, then please ask me more about this later. And finally, something that Atri and Tirth have really led is how these first galaxies can also be used to say something about the nature of dark matter. Again, in the interest of time, I'm not going to talk about this, but if you're interested, please do feel free to raise this question. So we have used data from ALMA, from the James Webb, to try and answer all of these questions to baseline our models as we look forward towards the era of Euclid, SKA, and of course, LISA. Okay, so the structure of the talk is going to be, I'm going to give you a very quick overview of this interplay between galaxy formation and reionization to try and motivate why we need to model these two processes together. I'll give you a very quick overview of some of the puzzling physical properties that have been emerging over the past 2 years or so from ALMA and the James Webb. And finally, I'll try and show you how we can actually use the SKA to try and probe the patchiness of reionization. So let's start with the first part of the talk, which is trying to understand this interplay between galaxy formation and reionization. So at the 0th order, when we want to understand the process of reionization, if you really want to do the 0 level, what we are basically trying to ask is what is the fractional volume of the universe, which is filled with ionized hydrogen. As you can imagine, this is driven by a source term, where the first part, the box in red, is how many ionizing photons are early galaxy populations actually producing per co-moving volume. So here it could be from star formation, it could be from black holes. We don't make any assumptions. This is just how many photons do these early populations actually manage to produce. Now, as you all know, galaxies are really complicated environments, so only a very small fraction of the photons that are produced within a galaxy can emerge out. So this is what is called the escape fraction. And these two terms together determine how many photons that are produced emerge from these early galaxies to contribute to reionization. Now, if you look at the second term on the right-hand side, this is a recombination term, which is driven by the fact that when you have patches of the universe which are very dense, you reionize them, but they can recombine on short time scales. So you may have to reionize them multiple times. So as you can see, this basically depends, this recombination timescale depends on the clumping or the overdensity as a function of space and time. In the interest of time, I'm not going to talk about this recombination term, but I'm just going to focus on the source term, and I'm going to show you what are the key issues we are facing even in trying to model the source term. Okay, so let me make a really simple assumption. Let me assume all of the ionizing photons at high redshifts come purely from star formation. So what I can do is I can use the star formation rate density or the star formation rate per co-moving volume as a proxy for how many ionizing photons are actually produced within galaxies. So this is what I'm showing you here, the star formation rate per co-moving volume as a function of redshift. All of the points that you see here are from observation. So this is ground plus space-based observations. What you can immediately start to see is that up to a redshift of about 8 or so, all of these different observations are really in good agreement with each other. However, as we push to higher redshifts, so a lot of this data comes from lensing, which has its own systematics associated. As you go to these high redshifts, you can see that the data is equally consistent with a star formation rate density that falls off as steeply as 1 plus z to the power minus 11, or which falls off as shallow as 1 plus z to the power minus 3.5. Basically, this means that as of now, observationally, we don't really have a constraint on how many stars are forming per co-moving volume at redshifts above 8 or so. The situation is no better when we look at theory. So here I'm showing you results from 3 different kinds of theoretical models: semi-analytic in black, semi-numerical in gold, hydrodynamic in red. And what you can see is that these models basically cover all of the space that is allowed by the observations. So the point I would like for you to take away is that the star formation rate density remains really poorly understood at these high redshifts. And we are really looking towards instruments like the James Webb to try and tighten constraints to tell us the star formation rate density in the first billion years. Okay, the second issue that we are facing, so this is really the first part of the source term: how many ionizing photons do you produce? The second part is how many of these can actually come out of the galactic environment. So now let me show you the situation with the escape fraction. So here, this is the log of the escape fraction as a function of redshift. Again, these are all observational points. I'm not putting any theory here at all. What you can immediately start to see is that, so a given color represents the observations from a given group. What you can start to see is that for observations at very similar redshifts, for very similar kinds of galaxies, depending on their intrinsic properties, depending on the line of sight, for example, the escape fraction can be anywhere between 1% to as high as 100%. So as of now, the escape fraction, especially at high redshifts, at redshifts above 3 or so, remains extremely poorly understood. So this is the first problem that we encounter when we model the source term. The second problem is that reionization can have a severe feedback effect on galaxy formation. So here, let me explain what I mean. This is just a cartoon of reionization. So the blue and the pink colors that you see is hydrogen, which is neutral. So this is basically, you can assume this is at the ambient CMB temperature. The brownish patches that you see are ionized hydrogen. So here the hydrogen has been ionized, so the temperature can rise up to about 20,000 Kelvin. So at a redshift of roughly 10, let's say, the ambient CMB temperature is of the order of 30-ish Kelvin. But in regions that are ionized, it has risen by almost 3 orders of magnitude to 20,000 Kelvin. Basically, what this means is that if you have low mass galaxies, which are forming in regions that are ionized, they are hit by this high temperature background, because of which they can lose some or all of their gas. And so this is basically called the photoevaporation feedback from reionization. Now, if low mass galaxies lose their gas, we know these are the most common sources in the universe. So basically what is going to happen is once they lose their gas, they stop forming stars. And so they can really affect the progress of reionization. However, the problem of reionization is really a problem of computational scale. So for us to get a proper estimate of the global topology of reionization, it has been shown that we need to simulate volumes which are of the order of 200 co-moving megaparsec whole cube. However, galaxies are forming on 100 parsec scales, and the molecular clouds where you are actually producing your escape, your ionizing photons, which are going to determine the escape fractions, these are on the scales of 10 to 100 parsecs. So if you really want to couple the process of galaxy formation fully with reionization, you need to have simulations which go over 6 orders of magnitude in terms of physical scale. So this is basically the computational challenge of simulating the process of reionization from its first principles. So this is really computationally implausible. And so because of this, people have taken a lot of different kinds of approaches to try and get around this process. So this is a compilation that we did for a review, which we did in 2018. So I'm really sorry, but this is all very out of date. And I apologize if I've missed your favorite simulation. But basically, this is just to give you an idea of the sorts of models that are available. So for example, we have small scale models, which are really simulating galaxies on even down to their virial radii. So these are really trying to simulate the internal galaxy physics, which is happening, which is maybe driving the escape fraction. So these are fantastic for galaxy formation, but you cannot really use them for reionization because the boxes are just too small. We have intermediate scale models that are basically focusing on the large scale reionization, on the large scale galaxy formation process. Again, they are less than the size you need for reionization to really start converging. Now, then we have finally a number of extremely large scale models. So you can see these go up to 0.5 gigaparsec, but they are so large that they really don't resolve the sources of reionization, which are these tiny galaxies that are sitting at high redshifts. So to get around this problem, we created a framework which we call Astreus, which is on 230 megaparsec scales and can resolve down to 10 to the 8 solar masses in halo mass. And this is basically what I'm going to talk to you about now. So this effort has been really driven by two postdocs, Anna Hutter and Graziano Ucci, who have really been instrumental in developing the framework. So the idea is as follows. We need a large-scale simulation which can resolve the key sources of reionization. So we have followed a hybrid sort of an approach. So this is a semi-numerical model for reionization, where we start with very high resolution n-body simulation, so 3,840 cube particles, and the box size is 230 megaparsec, so we really converge on the topology of reionization. For all our dark matter halos, we identify how they have assembled through time, and to couple the baryonic properties, we use a model of galaxy formation, which I developed, which is called Delphi. Once you know the physical properties of each galaxy, you make assumptions about the escape fraction. So this is really the only free parameter we have to generate the reionization fields. Then at every step, you look at the impact of reionization back on galaxy formation at the next redshift step. And so this is really a fully coupled process of galaxy formation and reionization. And this simulation runs from a redshift of about 110 down to a redshift of 0. So the results have been published now in a number of different papers where we have looked at everything from cosmic variance for surveys with, for example, the James Webb, to the sources of reionization, the physical properties of these galaxies, the impact of black holes on reionization, and also looking at laminar emitters, which I'm going to talk about in a few minutes. So just to give you an idea, this is what a typical merger tree looks like. So this is the standard hierarchical picture of structure formation, where at high redshifts, you start from low mass halos, which are going to merge through time to form larger and larger objects. We have all the key processes of gas and stellar mass coming both from mergers, from accretion, star formation, which is really based on the potential of the halo or on the gravitational potential. And so this model is extremely stable. So you can basically use this in any n-body simulation and it should mostly always converge. So this is a key strength of this model as compared to others. We account for the fact that different stars explode at different times. So supernova feedback depends on the age of the star that you are looking at. We have full prescriptions for black hole seeding growth. We have many different feedback prescriptions for reionization, many different prescriptions for the escape fraction, chemical enrichment, and now also dust. So I can't go into the details of everything, but what I would like to show you is just one key result, which is that we can actually start to look at the impact of the underlying density field on the assembly of galaxies at different redshifts. So what I'm showing you here is the density field, which is just the dark matter density field, the reionization field in the second column, the stellar mass function in the third column. So this is just how many galaxies do you have of a given stellar mass, and the UV luminosity function, which is how many galaxies do you have of a given UV luminosity. So here, what we were really trying to highlight is the fact that all of these lines that you see are color-coded by the local overdensity. So if you look at an overdensity of 0, an overdensity of 0, this is a factor 2 more overdense than the cosmic density. All the results that I'm showing you are for these tiny boxes. So these are the Jade's deep fields, which is one of the key fields that is targeted. This is one of the key James Webb observations. So you can see these are really, really tiny fields in the sky. So of course, the idea is that when you target really tiny patches of the sky, there will be a huge impact of cosmic variance on your observables. So this is what we were trying to highlight here, that depending on the local overdensity in these tiny patches, the amplitude of observables, of key observables, like the stellar mass function and the UV luminosity function, are really going to change as much as by a factor 5 to 10. So if you look at really overdense regions, Galaxies seem to assemble and form stars at more or less the same rate, but you just have fewer galaxies. And so the local environment that the galaxies actually live in is really going to have a huge impact on determining their observables. And this is something that we are really trying to test now with James Webb observations. Another important thing that I would like to point out is if you look in the last panel, observers use something called a beta slope or alpha or beta, whatever you want to call it. This is basically the slope of the UV luminosity function between roughly minus 15-ish to minus 18. So this is just the slope of the luminosity function. What we tried to do was to quantify this slope as a function of redshift. All of the open points that you see are observables, where we already have estimates of these beta slopes at a given redshift. You can see the error bars are extremely large because these are very hard observations. And what we have tried to do is to look at the evolution of this faint and slope of the luminosity function in different kinds of scenarios for reionization feedback. So the red model is one in which reionization feedback is the highest that you can imagine. So we call this the maximal effect of radiative feedback. We assume temperatures which are extremely high, 40,000 Kelvin, and we assume that reionization can impact galaxies instantaneously. So this is really the upper limit that you can achieve for reionization feedback. Now, the more feedback you have for your low mass galaxies, the less stars they are going to form. And so basically what we are finding is that higher is the radiative feedback, shallower is this faint and slope of the UV luminosity function. If you assume a more gentle model for reionization feedback, so this is the green line, you can see that the slope is actually much steeper. So this is something that we already anticipated with TIRT in 2019 with our analytic models. And what we are showing here again is that if we can integrate down to magnitudes of minus 15 with the James Webb, which is really well within its capabilities, above a redshift of about 9 or so, we can really start to demarcate between different kinds of models of reionization feedback. This has to, however, be done in different fields because of the effect of supernova feedback. So supernova can also affect low mass galaxies. But if you imagine that the effect of supernovae is kind of model independent or environment independent, if you do this kind of an experiment in multiple fields, then the faint and slope can actually give you a very good idea of the impact of the ionization feedback back on galaxy formation. We also tried to look at the key sources of reionization and how many of these can actually be observed with the James Webb. So here what I'm showing you is the cumulative emissivity or the cumulative number of ionizing photons as a function of the UV magnitude. So these are really faint galaxies. These are really bright galaxies. If we look at a redshift of about 8, we find that about 80% of ionizing photons are coming from galaxies which are less luminous than minus 18. So these are galaxies which are forming stars at less than 1 solar mass per year, roughly. And they have stellar masses which are below 10 to the 9-ish solar masses. So no matter what we do, what we are finding is that low mass galaxies are the key sources of reionization. And this makes it even more imperative to really be able to model this interplay between galaxy formation and reionization, because as we just discussed, reionization has the most significant impact on these galaxies. Now, the problem is the following. So this was all baselined against the observations that we had from Hubble, from Spitzer, from the VLT. However, what I would like to show you is that over the past 2 years or so, from ALMA and the James Webb, we have had a number of extremely puzzling observations. So let me start with the first observation, which is the unexpectedly high dust contents of early galaxies. So this is something that we have done as part of the ALMA Rebels large program. What I'm showing you here is the dust mass as a function of stellar mass for galaxies at a redshift of 7. The green points that you see are the ones we had before our ALMA observations, and the blue points are what we have added as a result of this Rebels program. So this is 40 galaxies at a redshift of 7. Now, if you look at this plot, the first thing that will strike you is that the dust masses are basically independent of the stellar mass over more than 2 orders of magnitude. This is in contrast with any theoretical model. So all of these lines that you see here are different models of dust production, astration, destruction. No matter what we do, theoretically, we always find that the dust mass should basically scale with the stellar mass. And here I would like to acknowledge the work that has been done by Laura Samovico, who is a PhD student in PISA. So now this creates a problem that how do we explain these enormously high dust masses for these early galaxies? So for example, for some of these low mass objects, the dust to stellar mass ratio can be as high as 1%, which is higher than what we see in our very own Milky Way. Remember, these are galaxies at redshift 7, so well within the first billion years. So why are these objects so dusty? There are a number of different explanations which have been proposed. The first one is that we are really underestimating the stellar masses. So these galaxies could actually be much more massive, remains to be seen. Or we are really missing some key physics about dust processes, especially at these high redshifts. Now you would say, well, why would I care personally about dust? The reason we care is because what I'm showing you here is the fraction of UV light, because this is what we generally measure from these high redshift galaxies, the fraction of star formation that you see in the UV versus total as a function of the total intrinsic star formation rate. Again, the blue points are what you see from Rebels. And what you can see is if you even ignore every theoretical model, it doesn't really matter. We are basically missing 20 to 40% of star formation in UV. And this is just because it's attenuated by dust. So this immediately creates a problem that if we cannot really pin down the star formation rates, even of massive galaxies, how are we going to know how many ionizing photons are being produced at high redshifts? So this really is the first complication that we are now struggling with these unexpectedly high dust masses and attenuations, which were really unexpected, especially within the first billion years. The second problem is that from James Webb, it seems we have an overabundance of bright galaxies at these early epochs. So what I'm showing you here is the number density of galaxies per co-moving megaparsec as a function of the observed UV magnitude. So this is nothing but the UV luminosity function. Again, these minus 17 or so is faint galaxies, go towards minus 25. These are really bright galaxies. If you look at the point at so GNZ 11 has now been confirmed to be at redshift 11. We have other candidates between redshifts 10 and 13, which have not yet been spectroscopically confirmed. Even ignoring these, all theoretical models are basically predicting a UV luminosity function which falls off by a magnitude of roughly minus 20-ish or so at a redshift of 11. But GNZ 11 really lies on this extrapolation of the UV luminosity function. So it's much higher. The number density for this luminosity is much higher than anything any theoretical model is predicting as of now. The situation is complicated by the fact that the James Webb is now finding galaxies as high as redshifts of 16.5 or so. Again, what we would predict theoretically is these solid lines down here. So the question is that early observations with the James Webb seem to indicate an overabundance of massive galaxies at all redshifts, going at redshifts higher than 11 or so. And this is orders of magnitude higher than anything theoretical models are predicting. So now you could, well, this is inside information, but I will just tell you that the 16.5 galaxy seems to be actually a lower redshift quiescent dusty source. Fine, solving the problem. So this is actually at a redshift of about 5-ish. However, the problem still remains for galaxies that we are beginning to confirm spectroscopically at high redshifts, that there are just too many of them compared to what any theoretical model was predicting. I would just like to end this sort of part by saying that spectroscopy is really crucial. So there has been, I'm sure you have all seen all of these papers coming out from James Webb where it seems like we broke lambda CDM, but this is really not true. I think a lot of caution has to be exerted. So this is something we undertook a couple of months ago with Nathan Adams, where we undertook a comparison of the redshifts we would infer with different kinds of model fitting compared to the published redshifts in other works. So here, what I'm showing you is 16 galaxies which are behind the SMACS in the SMACS field. The redshifts that were inferred by Akim and the redshifts that we inferred. What I would like to point out to you already is that for a majority of sources, we are able to fit them actually with really low redshift quiescent dusty galaxy solutions. Some of the highest redshift candidates that people are claiming are actually really comparable with extremely low redshift quiescent dusty objects. So I would urge a lot of caution in interpreting these observations unless we really have spectroscopic confirmation. So this is happening over the next couple of months or years. And so this is really going to be a very crucial aspect in extending our knowledge of galaxy formation well within the first billion years of the universe. So with these sort of, with this sort of a background, let me now work my way towards probing the topology of reionization. And this is exactly where the SKA is going to come in, which is going to be crucial for pinpointing the topology of reionization. So for this, we are using a class of galaxies called Lyman alpha emitters. So these are just galaxies which have a visible Lyman alpha line at 1216 angstrom in the rest frame of the galaxy. So the issue is as follows. Lyman alpha, as you can see here, has a very high optical depth against neutral hydrogen. So if 1 part in 10 to the 5 of your hydrogen atoms are neutral, you basically get an optical depth of 1. So this is a very, very sensitive tracer of the neutral fraction. So the idea is as follows. Let's say you have all of these galaxies which are sitting in a largely neutral medium. If you have, for example, if you consider this galaxy, which I'm pointing at, produces Lyman alpha photons, they come out of the galaxy, they immediately encounter neutral hydrogen, so they get scattered out of the line of sight. So this galaxy is not going to be visible as a Lyman alpha emitter. On the other hand, if you have sources which are sitting clustered together, they can build a large ionized region. If the region is large enough that Lyman alpha can be redshifted out of resonance with neutral hydrogen, some or all of these galaxies can be visible as Lyman alpha emitters. So the idea is that in the initial stages of reionization, clustered galaxies are preferentially visible in Lyman alpha, with more and more field galaxies become visible as you come towards the end stages of reionization. So this is something that we were actually able to observationally confirm in 2016. So what I'm showing you here on the left-hand panel is our simulation results. So these are 2 Lyman alpha emitters detected at redshifts of about 7 in the Bremer deep field. And we predicted that these were only visible because they were clustered with a lot of faint sources sitting around them, which are not visible in Lyman alpha, but you can look at them in the UV. So we got time on the Hubble, and this is the number of galaxies around these 2 sources as a function of their apparent magnitude. So this is not really important. What I would just like for you to note is that based on generic estimates of the luminosity function, we expected to see less than 1 or 2 sources which were clustered around these 2 Lyman alpha emitters. Our models predicted that this was not true. For these to be visible in the Lyman alpha, you should have had of the order of 10 galaxies, 10 sort of faintish galaxies sitting around these Lyman alpha emitters. And we were actually able to confirm 8 of these. And so this was one of the first evidences that indeed, in the initial stages of reionization, clustered galaxies are preferentially visible in the Lyman alpha. So how is this useful for us? So this is precisely what we are trying to do for both the SKA and Euclid epoch of reionization groups, which I'm leading. And the idea here is as follows. Again, a cartoon picture of reionization. All of the black patches are regions which are neutral. So here, this is where you would get your 21 centimeter emission from. This is basically what the SKA is hoping to map out. On the other hand, where you have all of these ionized regions, which are these grayish regions, where your galaxy populations are sitting, and the galaxy populations are shown by these pink dots, these can actually be probed by instruments like Subaru, James Webb, the Roman, and Euclid space telescopes. And so the idea here is that if you can somehow cross-correlate data from 21 centimeter and the underlying galaxy population, then you can really build a strong model, or this is actually one of the only ways of getting hints on the topology and the sources of reionization in one go. So we have already started to do these calculations a couple of years ago. So this is from 2017. Where what I'm showing you is the 21 centimeter Lyman alpha correlation as a function of physical scale. There are 3 different models that are plotted here because we were comparing all of these different models within the theory group. It's not super important to look at the different numbers because the trends qualitatively are very similar. So let me just point you towards the colored shaded regions. As we discussed, wherever there is neutral hydrogen, you don't see Lyman alpha because it gets scattered away. So the first thing you do is that you expect an anti-correlation between the presence of neutral hydrogen, or 21 centimeter, and Lyman alpha emitters. So here I'm showing you the anti-correlation for an IgM, which is half ionized, half neutral. Here is where we find the strongest anti-correlation. And this is because at this point, there is enough neutral hydrogen to provide a 21 centimeter signal, but you also have enough galaxies becoming visible in the Lyman alpha because really half of the universe is ionized. As you move towards a universe which is 75% ionized, the strength of the correlation decreases. This is because although more galaxies are visible in Lyman alpha, your 21 centimeter is losing power. Finally, when you come to a universe which is completely reionized, there is no correlation because now, although all of your galaxies in principle can emit in Lyman or be visible in Lyman alpha, there is just no 21 centimeter left to detect. So this is the global overall picture that we are expecting, that as we go from a neutral to an ionized universe, the strength of this anti-correlation, which we can actually probe with instruments such as Subaru and SKA, is going to decrease. Crucially, the scale at which this relation turns over tells you something about the bubble sizes or the reionization region sizes in which these Lyman alpha emitters are sitting. So this is something that we are already beginning to work towards with the MWA. So this is a work that was led by Kapteyn. And so the bottom line here is that cross-correlating 21 centimeter and Lyman alpha data should really allow you to differentiate between an IgM which is X% or Y% reionized. So now, of course, you would say, well, what kind of surveys do you actually need to be able to do this? So what I'm showing you again here is the 21 centimeter Lyman alpha correlation, now on a specific scale, which is about 5 megaparsec, as a function of the field of view or the volume on the top axis. So the issue here is that there is a sort of give and take between the Lyman alpha luminosity that you can probe versus the volume you need. So the key issue in really simple terms is the following. If you don't have too many Lyman alpha emitters, you have so much noise that your signal basically gets smeared out. If you don't have a large enough volume, again, you have too much noise. So just to summarize here, as the volume decreases, your thermal noise is going to increase. As the number of Lyman alpha emitters decreases, your short noise increases. And so what we were trying to do was to find optimal surveys which could maximize this correlation between 21 centimeter and Lyman alpha emitters. You can go extremely, extremely faint. So these are extremely faint Lyman alpha emitters with luminosities between 10 to the 41, 42. If you can't probe to this extent, which is really hard to do, you could actually go down to fields of view which are really small, so of the order of a few degrees squared, to try and differentiate between an IgM which is 50% ionized, 75% ionized, or 95% ionized. More probably, what is going to happen is we are going to probe Lyman alpha emitters down to about 10 to the 42 ergs per second. So this is a very typical limit for Lyman alpha emitters, which can be really easily done with Subaru. So for example, the Silver Rush surveys are already doing this. If you will consider these intermediate luminosity Lyman alpha emitters, you need volumes of the order of 25 degrees squared from the SKA to be able to really establish a cross correlation. What we are finding is that if we look at the brightest Lyman alpha emitters, so remember these are very few, so you are dominated by short noise. In principle, we will be unable to really distinguish between different ionization fractions, unless it's really 50% versus 10%. And so what we are proposing is the most optimal surveys to kind of optimize this correlation is really looking at intermediate luminosity Lyman alpha emitters over about 25 degrees squared volumes. Now, if you remember, I said that the escape fraction of ionizing radiation from galaxies is a key free parameter in our models. And so what we have tried to do is run our models. These are really fast, so they run on a few minutes to hour timescales, depending on what the different modules that you include. We have tried to look at two different kinds of escape fractions. So the top panel, the top row is for a scenario in which the escape fraction decreases with increasing mass. So low mass galaxies have a higher escape fraction as compared to high mass galaxies. The bottom panel is exactly the opposite. So the high mass galaxies have a higher escape fraction compared to low mass galaxies. Both of these are fully baselined against all of our reionization and galaxy observables. So both of these, in principle, on the global scale, both of these models are equally compatible with the data. What I would like to point out to you, however, is that the topology of reionization looks really different in these two different models. So for example, if you look at this panel, which is for redshift 7, you can see that your ionized regions are much more homogeneous when low mass galaxies, which are more homogeneously distributed, when they drive the process of reionization. If reionization is driven primarily by bright sources, then these ionized regions have a much more biased distribution. This is something that is going to be reflected in our 21 centimeter statistics. So in the interest of time, I'm not going to go into the details, but what I would like to just point out is that actually the escape fraction is going to have a much more important effect on 21 centimeter power spectra as compared to any other effects like radiation feedback or galaxy feedback. So with these models, we are really trying to work towards next generation models for the SKA. And here again, this is the same escape fraction, which I just discussed. So increasing with mass, in the lower panel, decreasing with mass. And what you can look at is the distribution of Lyman alpha emitting galaxies at different redshifts. So this is redshift roughly 8, 7, and 6.6. What is really crucial, so let's just look at this panel, which is redshift 7. If you compare these two panels, not only are the distributions of Lyman alpha emitters different, but also their luminosities are different. And this is because the line emission or the nebula emission is determined by 1 minus F escape. So the higher the escape fraction, less is the intrinsic luminosity that you produce. And so the most important point to take away is that when we try to do these correlations between Lyman alpha emitters and 21 centimeter, they are going to be really crucially affected by these parameters on really, really small scales, such as the escape fraction. So I think I've already gone over time, but I would just like to summarize by saying that what I've tried to do is to show you that galaxy observables are going to be extremely crucially linked to the underlying density field. So this is something we really have to take into account when we build models for reionization. We can already start using global observables to get a hint of reionization feedback. How you decouple this from supernova feedback is then a different process. Low mass galaxies seem to be the key drivers of reionization. But the escape fraction is going to be extremely crucial in determining the progress of reionization and also the visibility of galaxies in Lyman alpha. And this is a global overview. As we move forward, we have a number of fantastic instruments which are going to be online when the SKA is online. And this is going to include, of course, Euclid and also LISA. And so we will be in a fantastic position to try and link together not just global galaxy population. So this is in terms of what is the global statistics of your galaxies, but we can also start to combine this with our information on individual galaxy properties, such as their assemblies, dust formation, their gas masses, star formation rates. These together are going to have an extremely crucial impact on 21 centimeter cosmology, especially in terms of the sources of reionization and the topology of reionization. And of course, as we move forward, we are, of course, interested in trying to link this to the era of gravitational wave astronomy, which is going to be, so the high redshift black holes that are merging are really crucial for LISA. However, something that I didn't talk about is that their growth is actually really dependent on reionization, because if you have low mass galaxies which are impacted by reionization, their black holes will just not grow because they don't have gas. And so I really believe we are going towards an era where we can really start to build a complete picture of the first billion years of the universe, going from galaxy populations to 21 centimeter cosmology down to gravitational wave astronomy. And just to leave you with this ending slide, there is an Epoch of Ionization Synergy group where we are working very hard to try and link together the 21 centimeter emission we will see from the SKA with the underlying galaxy populations from different instruments. So this also includes quasar populations to shed light on the topology and progress of reionization. As of now, we are trying to discuss with the Subaru, WFIRST, Euclid, and also the Roman teams to try and see what we can do. And you are almost welcome to join this. This is really an open collaboration for everybody. So if you would like to join in, please just send an email to either myself, Andrea Ferrara, or Eric Zackerson. So we are all three coordinators for this. And I will just leave you here. Thank you very much.
Yeah, thanks, Pratika, for the nice talk. Now it's time for a few questions, please. You can unmute and ask questions. Yeah. Yeah, please.
Thanks, Samir. Thanks, Pratika. It was
Hello,
really
dear.
comprehensive. Yeah, hi. So I had several questions, but let me ask one first, and then I can come back if there is time. So the picture of dust that you presented, I mean, it's really interesting that high mass galaxies at least are so much dominated by dust.
Yeah.
But if we believe that reionization is still driven by small mass galaxies, I mean, do you have to worry about dust while modeling reionization? I mean, from the viewpoint of reionization modeler, I'm asking this.
Yeah, no, this is such a good question. So, maybe I can just show you this. So this is the star formation we are seeing in the UV versus the total as a function of the total star formation. So if you believe that galaxies, these low mass galaxies, which are typically their star formation rates are less than roughly 1 solar mass per year, we are going to basically miss 30% of the intrinsic star formation if we observe it in the UV. So, maybe 30% is not such a big deal, but I think it's still not really negligible. And I think the key problem is that we are finding it very hard to probe down into this low mass regime. So below 10 to the 9 is where we think we have the key sources of reionization, but this is exactly where the observation limits of ALMA kick in. So the lower blue shaded region, basically these are the detection limits for ALMA. So the whole problem is that we are kind of hitting our detection limits the moment we really move towards the sources of reionization. So we somehow have to extrapolate what we know about dust from these high mass sources, and we have to extrapolate it to the low mass systems. But I still think it's not negligible, and this is something we should worry about. And the best I think we can do is really baseline our models to the galaxies we can see, and then we kind of extrapolate to lower mass systems. Sorry, does this sort of answer your question?
Yes. No, I understand. Yeah. Thanks, Pratika.
Yeah, of course. Yeah.
Yeah, next. Yeah, Shumon, please.
Hi, such a nice talk. So I have a very naive question. So the plot you showed where you had the reionized 21 centimeter signal and the galaxies in magenta color.
This one?
This one, yes.
Yeah.
And in the next plot, you showed how they are anti-correlated. So this anti-correlation comes. So the question is, sort of I'm puzzled by this. So when you are actually observing the signal, you won't get any 21 centimeter signal from those patches which are like grayish that you made.
Yes, exactly. Yes.
Right. So you will have only 21 centimeter signal coming from the black regions, basically.
Yes, that is correct. Yes.
So how do you estimate the anti-correlation experimentally? Like in the simulation, I understand you can get a mean and then get an over density and under density in terms of brightness temperature. But from observation, how do you plan? Like does it done?
Yeah, Suman, this is a very, very good question. So, like basically the way you have to do it is you have to do it as a function of scale, like as I was showing here. So this is a function of physical scale. So what is going to happen is, let's say you look at these galaxies, they are visible in Lyman alpha.
Right.
Close by them, you will not see any signal.
Right.
As you go farther and farther away, you will start to see 21 centimeters. So when you do this on global scales, these two things will be anti-correlated. Wherever you have the sources of ionization in principle, I mean, like it's in really simple terms, wherever you have galaxies, you will just not see 21 centimeter. So you have to basically cross-correlate two different data sets as a function of physical scale, and this will basically give you this sort of anti-correlation. Sorry, does this sort of answer your question?
Right, I understand. But it's sort of, so sorry, maybe I'm missing something. So when you are doing the cross correlation, you don't have any signal in the 21 centimeter in that scale. So how do you get the anti-correlation?
Oh, because when you go farther away, then you will start to see 21 centimeter, right? So
oh, okay. Now I understand. Thank you.
So I center my observations here, but then when I go out on larger scales, I will start to see 21 centimeter.
Okay, I understand.
And so this actually, the distance at which you start to see 21 centimeter, this actually tells you something about the bubble sizes that these galaxies are in. So this is basically what I was trying to show, that close by, there will be like, I mean, if there is 21 centimeter, yeah, okay, you will find something, but basically the scale of turnover tells you that the density of hydrogen or the 21 centimeter strength is rising. And this tells you something about the bubble sizes that these galaxies are living in.
Okay, yes, I understand. Thank you.
Perfect. Yeah, of course.
Yeah, Purul. Burun, please unmute and ask questions. Yeah.
Am I audible?
Hello.
Hello.
Yes.
Yes. Yeah.
Yes. So nice talk. So I was just wondering that when you are showing these two cases for escape fractions, so one is from the lower mass, and so with the present observation, so what's the expectation? So can we distinguish between these two scenarios?
So Varun, I would say as of now, we cannot. Because the reason is that we don't have any topology of reionization as of now. Like all we have is some sort of an upper limit on the 21 centimeter power spectrum. But as of now, we really don't know anything about these ionized patches. And you can kind of try and infer something from Lyman half emitters, as I was showing you, but as of now, both of these are kind of equally compatible. So right now, we don't have any really strong observable to be able to distinguish between these two. And especially because when people are looking at the escape fractions from individual sources, I mean, they range anywhere from like 1% to 100%. So right now, I mean, it's a really, really good question, but I think we really need something like 21 centimeter to be able to distinguish between these two scenarios.
Even with luminosity functions or something like that, it's not possible.
No, because the problem is that you can try to do this. Sorry. So as I was showing you, so this is something that Tirth and I were trying to do like years ago. So depending on the topology or the escape fraction, you will have different feint and slopes in the luminosity function. But as of now, both of them would be more or less equally compatible with the data.
Okay.
And it's just because really, I mean, we don't have any constraints above redshift 8. And you can look at the constraints, right? I mean, the error bars are like a 1. So it's basically, it allows anything between, which is a slope of -2 to a slope of -3. And so even with this luminosity function, I mean, these constraints are really, really poor. So with these, you can really not do this. As I was trying to show you, like look at the error bars that we have on the galaxies we are observing right now with the James Webb. So the error bars are just too large to be able to do anything. And remember, these are the brightest sources. What we want to do is look at sources which are like here at -15 or so. And these are really hard to detect at high redshifts. So I think probably,
As you are showing this plot, so I am just wondering, so what kind of models will you need to account this kind of detection at 16.5 or so, this bright?
Yes, well, that is a really good question. Yeah, so like the models which work with this is it's really a very strange upper limit. So this is if you take your halo mass function, you assume all your galaxies have a cosmological gas fraction, and 100% of that gas forms stars. So this is what we mean by 100% star formation efficiency. So these are really the upper limits of what any theoretical model can predict. Yeah, so these are really extreme limits, right? And this point basically sits on this extreme upper limit. So, I mean, I think the problem now is getting resolved because this galaxy was spectroscopically targeted on Tuesday. And I think probably by next week, this paper should come out that this is actually a much lower redshift source. So this is at a redshift of 5.
Oh, I see.
Yeah, but it still leaves the problem, for example, for GNZ 11, which we know is spectroscopically, we know it's at redshift 11. And so this is kind of tricky.
Yeah. So I have another one. So,
Sure.
so when you are telling that escape fraction is dominating over the feedback effect while you kind of tell about the power spectrum. So, but the feedback will also have different strengths, like it will also depend upon how much heating is going on.
Yes, exactly. Yes. So here what I'm showing you is the black and the yellow models. So this is like a zoom in for this. The black and the yellow models are for maximum and minimum reionization feedback with a constant escape fraction. The red line is for an escape fraction which decreases with increasing mass. And you can see that it predicts like a slightly different, it predicts a lower amplitude of the 21 centimeter, so within error bars, I'm not sure we can really distinguish between them. But I think the key point is the following, that the escape fraction actually is crucial in determining also reionization feedback. So let me give you an example here. On the top panel, really, so this is low mass galaxies, which are driving reionization. So you can see that the ionized patches are much more spread out at every redshift, right? So when you have low mass galaxies forming in these ionized regions, they are already feedback limited earlier on. And so the problem is that, like the escape fraction is not just driving the topology of reionization, but also the feedback from reionization. And so this is why we find that this is actually a more crucial parameter than just the effect of reionization feedback. Sorry, does this sort of make sense?
Yeah, sure. Thank you.
Yeah,
Thanks a lot.
Oh, yeah, of course. You're so welcome.
Any other questions? Yeah, I have one. So the 21 centimeter alignment for this cross correlation, which redshift will be important? What is the redshift range?
Samir, this is such a good question. So, like a few years ago, I would have said 7 because we were convinced that the midpoint of reionization was kind of like 7. But if I understand from the Quasar people, and I think Tirth is probably more of an expert than me, it seems now the end point of reionization has shifted to redshift 5 instead of redshift 6. And so, yeah, I mean, I think somewhere between 7 and 9 probably is a good point to target.
At the mid of the reionization.
Roughly, but the problem is that at redshifts above roughly 7.5, there is a severe drop in the number of Lyman alpha emitting galaxies. So observationally, between 5.7 to 6.6-ish, the luminosity function is kind of constant, then it just drops. And so we can go to redshifts higher than 7-ish, but it's just we will not have enough Lyman alpha emitters. So you will really be dominated by this kind of short noise.
Okay.
So it's not just 21 centimeter, but it's also the Lyman alpha part. So I would say something around 7 is probably the best. So that you are secure about having a sufficient number of Lyman alpha emitting galaxies.
Yeah. Okay.
Sorry, does this make sense?
Yeah. Okay, thanks. Akanksha, please.
Hello. Yeah, hi.
Hi.
So, I had a question from the clustering of Lyman alpha emitters would vary with redshift.
Yeah.
So would that redshift evolution impact the cross correlation, say for example, where the turnover happens and so on, and whether it is accounted for when we make these calculations?
Yes. So Meenal, this is such a good question. So yes. So how your Lyman alpha emitters are clustered is really going to affect this correlation. And this is something that is not published. I mean, while you can kind of see it in these models, But the problem with these were that they were really small scale. So all of the models shown here are on scales of less than 100 co-moving megaparsec. So we are not sure that the topology of ionization has converged. So this is why we are now trying to do this on much, much bigger scale. So now we are trying to do this on 250-ish megaparsec scales. And so, yeah, please stay tuned. This paper should be out soon. Yeah, but the correlation really changes based on the escape fraction. Yes.
Any other questions? I think no. Thanks, Pratika, for giving the nice talk. Yeah. Okay. Thank you all. Yeah. Okay.
Thank you very
bye-bye.
much, Amelia. Thank you. Thank you.